All right, the last of the four equations is this geometric gradient. And the idea is that most normal, more organic type of cash flows will be in a percentile increase. They will not come in a linear increase. That's something arbitrary that we generally, force into our contracts and things like that. But normally you see a geometric increase. And the idea is that you're going to see a percentile increase each year. We've already talked about one. For example, we can model the increased maintenance in facilities that are degrading, they're kind of old, as a 2% per year increase. Your builder system actually models increased degradations of facilities and the cost to maintain a facility on a percentile basis as well. So here's an example. AFCEC is considering at a strategic level, let's eliminate dry transformer maintenance. We will not do any more dry transformer maintenance out there. What a dry transformer is, it's a transformer that doesn't have like an oil-based cooling system or coolant in it. And pretty much they're inside of facilities. They generally have very low maintenance anyway. You go in there about once a year or so and you blow out all the cooling fins and all that stuff just to make sure that they don't have a lot of dust in them, kind of like what you do to your laptop, or you should do to your laptop. And clean that out there so that over time they don't overheat and it degrades the performance. There's other things you do and tests that you perform on it, but essentially that's one of the main type of maintenance activities you do with it. But for the most part, these things are generally very little maintenance that you got to do on them. By eliminating maintenance, they are expecting to save $1.5 million across the Air Force in maintenance. So each base is going to be a few $100s, whatever they do in maintenance, but across the Air Force, it's going to save $1.5 million. However, we expect across the Air Force, we'll probably lose a couple of transformers in the first year, and then every year thereafter we expect that to increase, because eventually in some of these mechanical rooms these things are going to get clogged up and they're going to degrade, and then they're going to go down. So 15% increase over that time period. What's the present worth of our failures, of our failure costs? Well, let's take a look at how we do this. We're looking at the fourth formula. This is for geometric gradients, and again, we're going to use these real interest rates that we have down here. And the equation is, it's a pretty big equation. It's probably the most complex equation, and the main reason it's the most complex is because we've got one more variable. We need to know the first year's maintenance, or the first year's cost. We need to know what the percentile increase is, that's the J, that's the gradient. And then we need to know what the interest rate and the total term of analysis is. So that's the N and the I. And we put it into this equation and we come up with what the present worth is. Now, because I minus J is in the bottom, that means I can't equal J. So what happens if I is equal to J in those rare occasions? Well, then if I is equal to J, you do A times N over 1 plus I, which is a much simpler equation. How likely is it that I will ask on the test an example where I is equal to N? Very unlikely. Okay, so you need to be prepared to be able to do this formula, because that's the most likely scenario you'll run into in the real world. So let's do a couple examples. What's the present worth of 10 years of maintenance on a decaying roof fabric? We're back to roofs, I'm sorry, but we're going to go back to roofs, and what is the present worth of 10 years worth of maintenance on that? If we expect it to be $500 this year, and we expect the annual increase to be 2% per year. Well, the I for 10 years is 1%. We can go back to that table, pull out that 1%. We take the first annual is going to be $500. We know the increase is 0.02. We know the interest rate is 0.01. So I is not equal to J, right? And we got the N value is equal to 10. Now we plug that into that equation. It's a big equation. There is a negative exponent in there. But it's an equation that you can do. You can work from the inside of the parentheses out. 1 plus I to the N is 1.02, or 1 plus J to the N is 1.02 to the 10th power. And 1 plus I to the N is 1.01 to the 10th power. We calculate all that out, and that comes up to a factor of 10.35397. And we multiply it against the $500, and it comes up to $5,176.99. Now, I want to show you something that you might have seen on a couple of these slides, and I kind of even scratched it up on one of the slides, and that is there's some nomenclature you're going to find in the engineering economics world, and that is we describe this factor as a P/A. That's not a division problem. Okay, I occasionally get, when I write P/A up on maybe a little chart, people think, well, that's a division problem. That's not. That's a P given A. That's what that means. P, the present worth, given the annual worth, and then they put in the other factors behind it. When you know those factors, you fill in those actual numbers. And so it's important that you kind of catch that nomenclature, because that's how we write it in a shorter fashion. Let's look at a second example. The Air Force is looking to bed down the B-21 at a particular base. And at this particular base, we're looking at a cost of the power requirements for whatever the mission requirements are. We know that the first year requirements are going to be $200,000, but over the period of this bed down is going to occur over 12 years. So let's say that's the length of the period. We expect that power requirements to increase exponentially. It's going to increase on the 3% rate. So we're going to use a term of analysis at 12 years, and then we also need to know what that annual increase is. That J, it's 3%. So what's the present worth of these costs? Draw out the cash flow diagram. It's going to be 12 years. N is equal to 12. And the interest rate, we're going to have to interpolate between 1.0, which is at the 10-year point, and the 20-year rate, which is 1.2. You can see that every year we get 0.02 increase in interest rate. So we'll figure out that interpolate comes up to 1.04% is the interpolated interest rate. And now we need to throw out that first year cost, $200,000, and then we need to figure out what that cost is as it increases each year, 3%. And remember, although the increase starts in year 2, we still use the full term. And also note that the interest rate is not equal to the J. So $200,000, we got the 0.03, we got the 0.0104 for the interest rate, and don't round that off. If I've got 1% at 10 years and I got 1.2% at 20 years, don't round everything off, because otherwise you're basically up to 15-year point, you're still using 1.0. And then beyond that, you're using 1.1 and then 1.2, and it just becomes, it's not really useful for you to determine which year it is. It's the same interest rate across the board. So $200,000 times 1.03 to the 12th power times 1.10, that's it, 1 plus the interest rate, 0.0104, to the negative 12th power. Plug that through your calculator, you come up to 13.229 times the $200,000, and you come up with $2,645,842. So percentile changes. Very common. You're probably going to run into these in situations where you've got increased maintenance or decreasing usage. Maybe you've got an operation that's closing down and you're going to get rid of so many people this year or so many people that next year. Whatever it is, you might run into a percentile increase or decrease. You can model that using the gradients.